Hello students, in continuation with our series on case studies questions, today we'll take up questions on electromagnetic induction. In this series, we have started our discussion with first one on what are case studies questions, why they have been introduced in the syllabus, and what is the best and proper way to tackle case studies questions. We have taken few sample questions there in that particular discussion. After that, we have started chapter-wise case studies questions discussion. In the first chapter, we have taken electrostatics. After that, we have taken discussion on case studies questions on current electricity. Then magnetic effect of current and magnetism. And in its continuation, today we are going to take case studies questions on electromagnetic induction. The first case studies question on electromagnetic induction. Currents can be induced not only in conducting coils but also in conducting sheets or blocks. Current is induced in solid metallic masses when the magnetic flux threading through them changes. Such current flow in the form of irregularly shaped loops throughout the body of the metal. These currents look like eddies or whirlpools in water, so they are known as eddy currents. Eddy currents have both undesirable effect and practically useful applications. For example, it causes unnecessary heating and wastage of power in electric motors, dynamo, and in the core of transformer. Let's take first question. The working of a speedometer of trains is based on the different options which are given: wattless current, eddy current, alternating current, and pulsating current. Now, this one is eddy current's application, speedometer. So, eddy current will be the correct option. Of course, here it is not mentioned there in the passage anywhere that working of a speedometer is based on the eddy current. This is from your knowledge on eddy currents. So, as I have already told you people that case studies questions will be there, which will give you a base of any particular situation or case there. Some data may be there in the passage, but many questions may be there where it will be using the concept and things which have been referred in that particular passage. Next question, identify the wrong statement. Eddy currents are produced in steady magnetic field. If magnetic field is constant in that, and if the flux is not changing there, in that case eddy current will not be produced. So in that case this appears to be a wrong statement. Let's see the other options also. Like the second one is that induction furnace uses eddy currents to produce heat. So this is a correct statement. Eddy currents can be used to produce braking force in trains. This is also a correct statement. Power meters works on the principle of eddy current. This is also correct one. So obviously the wrong statement is the first one, that is eddy currents can be produced in a steady magnetic field. Next question. Which of the following is the best method to reduce eddy current? To reduce eddy current, what we do, instead of using thick conductor, we use laminated sheets of the conductor. So let's see what are the different options given. Laminating core. Second one is using thick wires. Third one is by reducing hysteresis loss, and none of these. So obviously the first one is the correct option, that is by laminating core. Next question. The direction of the eddy current is given by the different options which are there. Fleming's left-hand rule. It's not a correct one. Biot-Savart's law. This is also not the correct. Lenz's law. This is the correct one. And the fourth one, if you take Ampere circuital law, this is also not the correct one. So Lenz's law is the one which is the correct one, which gives the direction of the eddy current. Because of Fleming's left-hand rule, you know that it will give you the direction of the force on a current carrying conductor which is kept in a magnetic field. Biot-Savart's law, you can use it to find magnetic field at a point due to a current element. and Ampere circuital law, which we take when we apply it to a closed loop to find magnetic field there due to different current carrying conductors there. Last one, eddy currents can be used to heat localized tissues of the human body. This branch of the medical therapy is called, now the first option is hyperthermia, then diathermy, inductothermy, and none of these. So here in this case, it is the inductothermy which is the correct option there. Let's take second case study question on electromagnetic induction. According to the Faraday's first law, whenever the amount of magnetic flux linked with a circuit changes, an EMF is induced in it. Induced current is determined by the rate at which magnetic flux changes. Mathematically, the magnitude of induced EMF in a circuit is equal to the rate of change of magnetic flux throughout the circuit. Induced EMF is minus rate of change of the magnetic flux. Here, if you see the diagram, one diagram is given that there is a coil and there is a magnet which is along its axis it is kept. It can be moved there so that there is a deflection in the galvanometer, because when you are moving the magnet, the magnetic flux linked with the coil will change, and in that case there will be induced current developed in the circuit. Now let's see the different questions which are there in this based on this passage. First question, on the basis of Faraday's law, the current in the coil is larger whenever the magnet is pushed towards the coil faster, when the magnet is pulled away from the coil faster. Third one, both A and B, and the fourth one, neither A or B. We have seen that induced EMF, this is your minus d phi by dt. So if it is your d phi by dt, it is the rate of change of the magnetic flux. So obviously the current, if you consider, it will be your E by R. And if it is your E by R, that means induced current will depend upon the rate of change of the magnetic flux. When you are moving the magnet towards the coil or you are moving away, and in both cases you are moving it faster, so obviously in both the cases there will be induced current developed there. So it will be large. That means both will be the correct one, because it is not said that which one is more there or which one is being moved, in which case we are moving it faster. So obviously we'll take that in both cases there will be induced current developed there, and current will be larger there because it is being moved faster. If you are moving it slow, in that case it will be less there. Next is the flux linked with a circuit is given as phi equals to tq plus 3t minus 7. The graph between the time and the induced EMF on the y-axis will be. Now, if you consider here, it is the flux and we want to find a plot between the induced EMF and time. So if I differentiate this one so that we can get a EMF, which is your minus d phi by dt. So this will be your minus t cube. So it is your 3t square. Then it is your minus 3 and minus 0. So that is minus 3t square plus 3. This is for EMF. This is not the equation of a straight line. It's not in the form y equals to mx plus c. So obviously in this case, the first one, a straight line through the origin is wrong. A straight line with positive intercept, this is wrong. Third is also wrong. Fourth one, it is a parabola not through the origin, because there is a one constant term, 3 is also there. So it is definitely a parabola, but not through the origin. So that means the fourth one will be the correct option here. Third question, wire loop is rotated in a magnetic field. The frequency of change of direction of the induced EMF is. Now you have a loop, you are rotating it in a magnetic field. So the frequency of the change there, because if you have the loop there and you are rotating in magnetic field, if magnetic field is from left to right, suppose, and coil is held perpendicular to that, that means this plane is perpendicular. So in this particular case, if you rotate it, so after half rotation, in that case, it will be again perpendicular, and then in one full rotation, it will once again come to the same orientation there. So here, it is coming to one particular that orientation twice there. So the frequency of the change of direction of the induced current, it will be twice per revolution. So this is the correct option, not once, not 4 times, not 6 times, it is twice per revolution. Now, next question. The instantaneous magnetic flux linked with a coil is phi equals to 5TQ minus 100T plus 300 Weber. The EMF induced in the coil at T equals to 2 seconds. Now, in this particular case, if I consider, you have to find the EMF. So, suppose if I take E, that is your minus d phi by dt. And if you put it, it is minus. Now, the differential of this 5TQ, this is your 15T square. And then it is your minus 100 plus 0. So this is your minus 15T square plus 100. Now, if you want at T equals to 2 seconds, what is the EMF there? So at T equals to 2 seconds, EMF will be your minus 15 into 2 square plus 100. So this is your minus 60 plus 100, and that is your 40 volt there. So now if you see the different option, second one is the correct one. So this will be the correct option there. Next question. A copper disc of radius 0.1 meter is rotated about its center with 20 revolutions per second in a uniform magnetic field of 0.1 Tesla with its plane perpendicular to the field. The EMF induced across the radius of the disc. So here, if you have a disc and you are rotating this disc about this axis where its plane is perpendicular to the magnetic field, in that case, the EMF which is developed across its radius, basically it is from center to a point on the circumference. So now if you take the EMF induced, it is your E as minus d phi by dt, and this is given as for the EMF which is developed. If you find out its expression, it will be ultimately half b omega L square. So this is for the EMF which is developed across the radius of the disc or across a conductor of length L which is rotated about an axis which is passing through one of its end and is perpendicular to its length. So in that case, it is your half b omega L square. It is same expression for the EMF when it is taken between the point on its axis, that is at the center, and any point on its circumference. So it is your half. For b value, it is given as 0.1. Omega is 2 pi and f is your 20 revolutions per second. So it is into 20, and then L will be your 0.1 whole square. So this is your 20 pi, because here 1, 2 will get cancelled. So it is your 20 pi, and then it is your 10 to the power minus 3. So it is your 20 pi millivolt. So if you look at the different option, one is your pi by 20, pi by 10, 20 pi millivolt. So the third one is the correct option. Next case study. In year 1820, Oersted discovered the magnetic effect of current. Faraday gave the thought that reverse of this phenomena is also possible, that the current can also be produced by magnetic field. Faraday showed that when we move a magnet towards the coil, which is connected by a sensitive galvanometer, the galvanometer gives instantaneous deflection, showing there is an electric current in the loop. Whenever relative motion between the coil and the magnet take place, and EMF induced in the coil. If the coil is in the closed circuit, then current is also induced in the circuit. And this phenomena is called as the electromagnetic induction. So basically, this is the details of the electromagnetic induction phenomena. And the diagram which is given here, you have a coil and a magnet is being moved towards its axis there. So there will be induced current. This is the galvanometer which is showing current there in the circuit here. Let's take first question. The north pole of a long bar magnet was pushed slowly into a short solenoid connected to a galvanometer. The magnet was held stationary for a few seconds with the north pole in the middle of the solenoid and then withdrawn rapidly. The maximum deflection of the galvanometer was observed when the magnet was. Now you see the movement of the magnet which is given here, that the magnet is moved along the axis of a short solenoid and it was held stationary for a few seconds with its north pole in the middle of the solenoid. And after that it is withdrawn rapidly. Now you know that EMF which is given as your minus d phi by dt, that means it is the rate of change of the flux. So the flux change will be maximum there when it is moved rapidly. So the maximum deflection will be there at that particular moment when there is a rate of change of the flux there associated with the coil or solenoid will be maximum there. So in this particular case, when it is different options which is given, moving towards the solenoid, moving into the solenoid, at rest, moving out of the solenoid. So obviously it is being withdrawn rapidly. It is mentioned there. So the fourth one will be the correct option. Two similar circular loop carry equal current in same direction. On moving the coil further apart, the electric current will be, first one is remain unaltered, increases in one coil and decreases in the second one, increases in both, decreases in both. You have two coils there. Suppose these are the two coils and it is mentioned that they are carrying equal current. Now when you are moving them apart, so if you move them apart, what will happen? The magnetic flux linked with them will decrease. And if the magnetic flux linked with the coils is decreasing, there will be induced current set up. And that current will be there in a direction to oppose the cause. That means it will try to develop a current there in the direction so that it can oppose that. Now suppose if they are carrying current, say both are carrying current in the clockwise direction. You are moving, suppose one of the coils, say this one, I call it as the first one, this is as second. So I am moving first coil away from it. So that means I am moving it away. So if you are moving it away, in that case, what will happen? The flux linked with that will decrease. And if the flux is decreasing, the induced current which will be set up, it will be in a direction so as to oppose the cause. That means it will try to increase the flux because the flux was decreasing. So in that case, it will set up the current in the same direction so that it can increase the flux there or compensate for the decrease of the flux. So it will set up current in the same direction. And if it is setting current in the same direction, what will happen? The net current in the circuit will increase. So it will increase in both. Because this same phenomena will happen with the other coil also. So it will increase. Let's take next question. A closed iron ring is held stationary and a bar magnet is dropped through the ring with its length along the axis of the ring. The acceleration of the magnet is, suppose you have a coil here and we take a magnet, suppose this is the magnet, which is north pole, south pole, and it is being dropped along its axis. As the magnet is falling along the axis of the ring, the magnetic flux linked with this ring will change. And in fact, it will increase. If it is increasing, it will try to set up the current, that is the induced current there in it, in a direction to oppose the cause. And for that, what is the cause there of the change of the flux? the movement of the magnet towards the ring. So in order to oppose, it should set up the current in such direction that it should produce a force on the magnet to oppose its motion. And its motion is opposed, definitely its acceleration will decrease. So in that case, the acceleration will be less than g. So let's see what are the different options there. Equal to g, wrong. Less than g, correct. More than g, wrong. Depends on the diameter of the ring and the length of the magnet. No, this is the second one, which is the correct option there. Next question. Whenever there is a relative motion between a coil and a magnet, the magnitude of the induced EMF set up in the coil does not depend upon. Now let's see what are the different options there. One is the relative motion between the coil and magnet. No, it's not that. Then the resistance of the coil. Yes. You have to opt for the case that the magnitude of the induced EMF setup does not depend upon. What are the factors on which it is not depending? So relative speed, definitely it will depend. Resistance of the coil, it is not depending upon that. Magnetic moment of the coil, definitely in that case, because there will be the current there and it will try to oppose. Number of turns in the coil, so this is also not the correct one because it will depend upon the number of turns there. So the correct option for this particular question will be the resistance of the coil, because the resistance of the coil will be the one on which the magnitude of the induced EMF will not depend. Let's take the next question. A coil of metal is held stationary in a non-uniform magnetic field, and different options are there, and EMF and current both are induced in the coil. Second one, a current but no EMF is induced. A current and EMF but no current is induced. And the fourth one, neither EMF nor current is induced. What is given there? It is given that a coil of metal wire is held stationary in non-uniform magnetic field. Remember, in order to get induced current developed in the coil, the magnetic flux linked with the coil or the ring should change. So if it is non-uniform and the coil is held stationary, it is not changing the flux. It may have a different value there, but that value will remain fixed unless you are changing the magnetic flux linked with the coil. So obviously neither EMF nor current will be induced in the coil. This was the discussion on some of the case studies questions on electromagnetic induction. We'll continue our discussion on few more case studies questions on electromagnetic induction in our next discussion.